Good evening, everyone. Okay, so last time we have learned about the basic concepts of sensitivity analysis graphically, right? And it's about how changes in an LPS parameter, such as objective coefficient and the right-hand side values for each constraint, affect the current optimal solution, right? And the sensitivity analysis is very important because all these informations can be determined from the original solution, okay, without solving the problem again. Okay, so last time, to illustrate the basic concepts of sensitivity analysis graphically, we have considered the window glass problem. And the complete math formulation for window glass example is like this, right? And this is the corresponding Lindo output for window glass example. And besides the optimal solution, the Lindo provides the information for sensitivity analysis, right? And last time we have learned about how both objective coefficient ranges and the right-hand side ranges are obtained graphically, right? And in Lindo output, the objective coefficient ranges indicates by this amount the objective coefficient can be changed without causing a change in the basis. So these are the ranges for optimality, okay? So the allowable range to stay optimal for the objective coefficient of x1 variable, for example, can be obtained. That is, the C1 must be greater than or equal to 3. This 3 is the current coefficient value from here, minus 3. That is the allowable decrease limit from here, right? And this C1 must be less than or equal to 3. Again, this is the current coefficient value, plus 4.5. That is the allowable increase limit, right? So we may say that within these ranges, the optimal solution remains optimal. In other words, within this range, the window glass should still manufacture 2 doors and 6 windows. That is the current optimal solution. Of course, the windows glass profit will change even in these ranges, okay? And graphically, we have shown that if all other parameters remain unchanged, within these ranges, the objective function coefficient may vary without changing the optimal solution, right? And Lindo output, the right-hand side ranges for each row are the amount by which the right-hand side value can be varied while the current optimal solution remains feasible, right? In other words, within this range, the set of binding constraints doesn't change. So this range is called for range of feasibility, okay? So the allowable range to stay feasible for right-hand side of the last constraint, for example, can be obtained like this. The B3 must be greater than or equal to 18, that is the current right-hand side value, minus 6, that is the allowable decrease limit. But this value, B3, must be less than or equal to 18, the current value, plus 6, that is the allowable increase limit, right? So within these ranges, the optimal solution remains feasible. And the binding constraints remains the same. Of course, we assume no changes occur in the other right-hand side values, okay? And last time we've shown that the right-hand side value of the third constraint can vary within these ranges, right? While the current optimal solution remains feasible. That is, within this range, the right-hand side value can vary without changing the current binding constraint, which means within this range, the optimal solution occurs at the point where the both constraints, both Planck number 2 and number 3 constraints are binding at the feasible region. Okay? That's what we've learned from last time. So, any questions about this? Okay, then today we are going to talk about the dual price. Okay? First of all, I want you to recall your memory. A couple of weeks ago, you've learned about how to interpret the dual variable economically, right? When you consider the primal dual pair. The dual variable represents the rate of change of the optimal objective value with respect to the right-hand side value. And it is also known as simplex multiplier, which is represented by pi, right? And the Lindo provides the value of dual price instead of dual variable for each constraint. And according to Lindo, the dual price represents the amount by which the objective function value would be improved given a unit of increase in the right-hand side of the constraints. Of course, the improve means the increase in the maximization problem and the decrease in the minimization problem. Is that right? So, in maximization problem, the dual price is dual variable. However, in the minimization problem, dual price becomes negative sign of dual variable. Okay? And this dual price are sometimes called the shadow price because they tell us how much we should be willing to pay for additional units of resource, that is the right-hand side value. Okay? And from Lindo, we've got 0. Let me choose the color. Okay. We've got 0 and 1.5 and 1 for the dual prices of each constraint, right? So these tell us if the right-hand side value of the last constraint, for example, if the right-hand side value of this last constraint is increased to 19 from 18, for example, then the objective function value becomes 37 instead of 36, right? Because the objective function value will be increased by this much to your price. Is that right? Okay, then what if the right-hand side value of last constraint is decreased to 17 from this value 18? Then what happened to the objective function value? The objective function value currently is 36, but it becomes 35, right? Because the objective function value will be decreased by this much. However, all these dual prices is valid only if the corresponding right-hand side value varies within the allowable ranges. Okay? So for example, let's consider the value of how could I delete all of this? Okay. Sorry. Okay, so for example, let's consider the value of 1 as the dual price for the last constraint. And this value remains valid only if the right-hand side value of the last constraints varies within this allowable range. Otherwise, the dual price of 1 doesn't mean anything. Okay? Is that a little bit complicated? We've learned that the right-hand side ranges for each row are the amount by which the right-hand side can be varied, while the current optimal solution remains feasible. Is that right? Or within these right-hand side ranges, the set of binding constraints remains the same. That's what we've learned so far, right? And we may also say that within these right-hand side ranges, the current dual price remains valid. Okay? So, like we did last time, here, let's say B3 is the number of available production time for plant number 3. And currently, the B3 is 18, right? Now, we will see the effect of a change in the value of B3 on the current optimal objective function value. Okay? I said the currently B3 is 18, right? So if we increase the right-hand side value of B3 by 1 unit, that is, if B3 is increased to 19, what happened? The objective function value will be increased by this much, the dual price. Is that right? So the objective function value becomes this value, 36, that is the current value, plus 1, that is from the dual price. Is that right? So the objective function value becomes 37. Does that make sense? graphically changing in B3 shifts the plant number 3 constraint parallel to its current position, right? So the new optimal solution occurs right here. This is the new optimal solution, right? With the corresponding objective function value of 37, okay? With the improvement of 1. Of course, the plant number 2 and number 3 constraints are still binding in this feasible region, right? And and the corresponding objective function value is improved by the dual price of 1, right? And now, let's suppose if the B3 is increased by 6, okay? So the right-hand side value is increased by 6. So it becomes 24. Then what happened? In this case, the increment of 6 is still within the allowable increase limit, which is 6, right? So we may say that the objective function value is improved by 6 times this much dual price for that constraint. So the objective function value becomes 36 plus 6 times 1, right? So this is 6. So the objective function value becomes 42. Okay, this is 42. And graphically, the new optimal solution occurs right here. Okay? With the corresponding objective function value of 42 with the improvement of 6, right? Of course, the plant number 2 and number 3 constraints are still binding in the feasible region. Is that right? Okay, then, now what if the B3 value is increased by 9 units, which is above the allowable range? Can we still say the objective function value is improved by 9 times this much? No, right? If the original optimal solution is feasible, then we can say yes. However, in this case, the original optimal solution is no longer be feasible, right? Because the plant number 2 and number 3 constraints are binding at an infeasible region, right? Because the plant number 1 constraint for door is not satisfied in this case. And you remember I said the dual price is valid only if the current optimal solution remains feasible. Okay? So in this case, we cannot use information about dual price anymore. Okay? So I would say we don't have enough information to answer this question. Okay? Okay, then now, what if B3 value, the right-hand side value for the last constraint, is decreased by 1 unit, which is within the allowable range, right? Then what happened to the objective function value? 35, yeah, decrease, right? The objective function value will be decreased by 1 times this much, right? Okay, let me choose the highlighter again. So in that case, the objective function value becomes 36, is the current value, minus 1. That is the dual price, right? So our objective function value becomes 35. Okay? And graphically, the new optimal point is right here with the objective function value of 35. And of course, this point, still, both plant number 2 and number 3 constraints are still binding in the feasible region, right? Okay, then what if the B3 is decreased by 6 units, which is still within the allowable range? In that case, the objective function value will be decreased by 6 times 1, right? This much. So the objective function value becomes 36 minus 1 times 6, which becomes 30. Is that right? The new optimal point is right here with the objective function value of 30. And the plant number 2 and number 3 constraints are still binding in the feasible region, right? Okay, then what if the B3 is decreased by 8 units, which is outside the allowable range? Can you say the objective function value is decreased by 8 times this much? No. In this case, the original optimal solution is no longer be feasible, right? And the plant number 2 and number 3 constraints are binding right here at an infeasible point, right? Because at this point, x1 value is less than 0, right? That is the infeasible point. And you remember, the dual price is valid only if the current optimal solution remains feasible. So in this case, again, the dual price is no longer valid, right? Okay, so in summary, the value of dual price is valid only if the corresponding right-hand side value is valid within the allowable ranges. Okay? And for the dual price of 1 for the last constraint, for example, this value of 1 is valid only if the right-hand side value of the last constraint is changed within these allowable ranges. Okay? And graphically, the dual price for the third constraint is valid only within these ranges of the right-hand side values. Any questions so far? Okay, then to illustrate sensitivity analysis of an LP problem, let's use a simple example called product mix problem. Okay? So in this problem, 5 products, A, B, C, D, and E, can be manufactured, and each product requires time on each of 3 machines. And this table shows the machine time requirement. And the unit is minutes per pound. Okay? So this is the machine time requirement. The unit is minute per pound. Okay? And 128 hours per week are available on each machine. Okay? And the variable labor costs are $4 per hour for machines 1 and 2, and $3 per hour for machine number 3. And any amounts which are produced may be sold at prices of $5, $4, and $5, $4, and $4 per pound for each machines, respectively. And the material costs for products A and C are $2 per pound, and for products B, D, and E, it is $1 per pound. Okay? And we'd like to determine how much of each product should be manufactured per week in order to maximize our profit. Okay? Okay, so first of all, we need to define the decision variable. Is that right? So how many decision variables do we need? 5. So how would you define the decision variable? Okay, yes. So basically, we need 5 decision variables, 1 for each product, right? And they are, okay. Decision variables, let's say A, B, C, D, and E. Those are the quantities of product A to be produced. And B stands for the quantity of product B to be produced, and so on. C, D, and E. And let's say the unit for each decision variable is pound per week. Okay? Then what is our objective? To maximize profit, right? So the maximize profit from manufacturing products A, B, C, D, and E. Is that right? Then how do you get the individual profit for each product? First, what is your profit?
Selling price minus cost.
Yeah, something like that, right? So profit, if you produce product A, can be obtained by selling price minus material cost, right? Minus labor cost, right? Variable labor cost. How much is the selling price for product A? That is $5 per pound, right? It's going to be $5 per pound, right? And the material cost is $2 per pound. Then how about the labor cost? Labor costs are $4 per hour for machines 1 and 2, and $3 per hour for machine 3, right? And each product requires machining time for each of 3 machines. And this table shows the machining time requirement. And I set the units at the minute per pound, right? So, for machine number 1, the variable labor cost would be $4 per 60 minutes, right? And this must be multiplied by 12 minutes per pound, right? Per pound. This is for machine number 1. And plus $4 per 60 minutes times 8 minutes per pound, right? These are the labor cost for machine number 2. Is that right? And plus $3 per 60 minutes times 5 minutes per pound, right? So if you combine all of these 3 terms, it becomes your labor cost for producing product A. Okay? And the labor cost becomes $48 per 60 minutes, right? No, 60 pounds, right? Plus second term becomes $32 per 60 pounds. The third term becomes $15 per 60 pounds, right? So the total profit, if you produce product A, becomes $85 per 60 pounds, which is $1.417 per pound. Okay? So the profit for producing product A is $1.417 per pound. Okay? Does that complicate? Okay, let's do this calculation for product B. The profit of producing product B becomes, again, the selling price, which is $4 per pound, minus the material cost, which is $1 per pound, minus the labor cost. Okay? And again, the labor cost for product B is for the first machine, machine number 1, the variable labor cost, which is $4 per 60 minutes times 7 minutes per pound, right? Plus $4 per 60 minutes times 9 minutes per pound. So we should look at this second row, right? Which is about producing B. And for the third machine, the variable labor cost, which is $3 per hour, which is per minute, per 60 minutes, times the 10 minutes per pound. Okay? So the minutes will be erased. This becomes $28 per pound per 60 pounds, plus $36 per 60 pounds, $30 per 60 pounds, right? And this becomes $94 per 60 pounds, right? So this value, labor cost, is $94 per 60 pounds, right? So the profit of producing the product B would be $86 per 60 pounds, which becomes $1.43 per pound. Okay? So this value should be the objective coefficient for variable B, right? Likewise, you may obtain the unit profit for each product C, D, and E. Okay? The same way. And our objective function becomes maximize 1.417. That is the dollar per pound, right? Times the decision variable A. The unit is pound per week. Plus 1.43 times A, and the unit becomes dollar per week, right? I'm sorry, that must be B, right? And 1.85 times C, dollar per week, and 2.183 times D, and 1.7 times C. Okay? Okay, then what constraints do we need to consider? Excuse me. There is a restriction on the machining time, right? Only 128 hours per week are available on each machine. Is that right? So for machine number 1, using these values, the constraint would be 12 times A, 7 times B, 8 times C, 10 times D, and 7 times E. These are the machine time required, right, for product A. No, that's the machine time required for machine number 1, right? Sorry. So this value must be less than or equal to 128 hours. Is that correct? Times 60. Exactly, right? Because the unit for the left-hand side is minutes, right? So what you need to do is multiply the right-hand side value by 60. Which becomes, the right-hand side value is 7,680. Is that correct? So it's the minute per week. So this becomes minute per week. Okay? And likewise, using these machining times for each machines, number 2 and number 3, we may construct other constraints, 8A, 9B, 4C, 0D, and 11E must be less than or equal to 7,680. These are for the machine number 2, right? And the last constraint would be using the third column, 5A, 10B, 7C, 3D, and 2E. It's less than or equal to 7,680 minutes per week. Okay? And each decision variable must be non-negative, right? So the complete LP formulation becomes like this. And this is because I've got this from the Lindo. The Lindo doesn't require us the non-negativity restriction, so it's missing right here. So all the variable must be greater than or equal to 0. So this is the complete LP formulation for this problem. Okay? Any questions about LP formulation for this problem? Okay. And if you use Lindo to solve this LP, you may obtain the optimal solution like this. And the additional information for sensitivity analysis, these are the objective coefficient ranges and the right-hand side ranges. And also, you may obtain the final optimal table like this, right? And we are going to use all of this information for sensitivity analysis, okay? And according to the Lindo definitions, the reduced cost of a non-basic variable is the rate of deterioration of the objective function as the variable is forced to increase by a small amount. Okay? That is, it is the rate of deterioration of the objective function values per unit increase, the value of the associated non-basic variable. So, in a maximization problem, like our problem, the reduced cost gives the rate of decrease in the objective. While in the minimization problem, the reduced cost gives the rate of increase in the objective. Okay? Of course, the reduced cost of a basic variable is always 0. Okay? In this problem, both variables C and E are the basic variable, and the corresponding reduced cost is 0. Okay? Okay, now let's suppose in our product mix example, it is necessary to produce 10 pounds of product A for the use as a sample for the customers, for example. Then what will be the cost in doing this? which means what will be the loss of profit in doing this? In the optimal solution, the value of decision variable A is 0, right? That is, the variable A is non-basic. And the reduced cost is 1.379667. Is that right? Which tells us the profit will be reduced by 10 times this reduced cost value. Okay? So, if you produce 10 pounds of product A, then your profit will be reduced by 13.79667. Does that make sense?
But you mean this are going to be 10 extra pounds?
Yeah, right. Because currently the optimal solution tells us you should not produce the product A, right? But we just suppose if you want to produce 10 pounds of product A, then in that case our objective function value will be decreased by 13.79667, right? Okay, now then let's suppose you want to produce 100 pounds of product D. Currently, the optimal solution tells us we should not produce product D. But what if you want to produce 100 pounds of product D? What will be the loss of profit in doing that?
100 times 9,
Right. The objective function value will be decreased by 100 times this reduced cost. Okay? Which means the objective function value will be decreased by 7.5333 dollars per pound. Okay? Actually, the unit becomes pounds, right? Because 100 pounds times this is the dollar per pound. Okay, whatever. Now you know how to use reduced cost. Okay? Okay, and according to the Lindau's report, the due price is the amount by which the objective would be improved given a unit of increase in the right-hand side of the constraint. And I said this definition applies only if the change in the right-hand side of corresponding constraint leaves the current optimal solution remains feasible, right? And I said the dual price is sometimes called the shadow prices because it tells us how much you should be willing to pay for additional units of right-hand side values. Okay, so in our product mix example, the optimal solution reported by Lindau includes these dual prices. Okay? By the way, is this the generate solution? No. Then how do you know? How many basic variables do we have in this example problem? Because we have 3 constraints, we must have 3, 1 for each constraint, right? And there are 3 positive basic variables. They are variable C, variable E, and slack variable for the last constraints, right? Which means this is not a degenerate solution. Does that make sense? And what is degenerate solution? For any basic solution, if at least one of the basic variable has a 0 value, right? Then we call it degenerate solution. And when there is degeneracy, what happens? The next basis change may not result in an improvement in the objective function value. Okay? And just refresh your memory. Okay. So, because the current optimal solution is not degenerate, this indicates that the profit will increase $0.225833 per additional minutes of available time on machine number 1, because the first constraint is about the machine number 1 constraint, right? And the profit will increase $0.010833 per additional minute of available time on machine number 2. Is that right? And if you look at the dual price for the last constraint, it is 0. So if a constraint is not binding, or if a constraint is not tight, which means if the slack variable or the surplus variable has a positive value in that constraint, then the dual price must be 0. Okay? This is a consequence of the complementary slackness theorem. But this is understandable in view of the economic interpretation of the dual price. That is, if a resource is not completely used at the optimum, which means if a constraint is not tight, like this, then the additional quantities of that resource will not result in increased profit or decreased costs. That is, the corresponding dual price must be 0. Okay? Does that make sense? And the Lindo output includes these objective coefficient ranges, right? And we've learned that in Lindo output, these objective coefficient ranges for each variable is the amount by which the objective coefficient can be varied without causing a change in the basis, right? And this range indicates how far the associated objective coefficient may change before the current solution values must change to maintain optimality. Okay? So within these ranges, the counter-optimal solution remains the same. In other words, within these ranges, both product C and E will be manufactured 512 pounds per week. And all other products, A, B, and D, will not be manufactured at all. Okay? Of course, the objective function value naturally changes when the coefficient changes. Okay? And the right-hand side ranges for each row tells us within these ranges of variable, within these ranges of values, the counter-optimal solution remains feasible. So some people say it is the ranges of feasibility. Okay? So, in other words, this right-hand side ranges indicates how far the limiting values may change while keeping the same optimum basis. And we've learned that the dual price or the shadow price remain valid within these right-hand side ranges. Okay? Of course, we assume no changes occur in the other right-hand side values. This is the right-hand side ranges provided by Lindo for our example problem. Okay? Okay, then this is all for today. And next time, I will continue to work on this product mix problem. So please bring the handout today for the next time. Thank you. I will see you next time.